So like first of all, I just wanted to have like a general consensus idea. How many have like a background in like cryptography? Like already done the basics, modular arithmetic, linear algebra. Okay. And how many have like worked with FHE systems like previously? Okay, yeah. So we'll keep the slide according to that. So like everyone has basically like achieves the same pace. So going through the developments which is basically happening in this fully homomorphic encryption space, we will cover several use cases, several algorithms which is basically used to achieve the homomorphic properties of the algorithms. Let's see how far we can walk with FHE. So a little bit about me. I'm currently building Banana HQ. And on a like hackathon corresponding, I have been like 2 times Heath Global finalist, and like previously I've been working with MathWorks and Just Network. And yeah, like I just started exploring this space like from past 2 to 3 months ago. So I'm not an expert. There might be like some issues or like some mistakes in this PPT. So pardon me for that. But we have our experts here, Janmay, Enco Network, Remy. They can help us. So just starting with the prerequisite, I think like I already conveyed the prerequisite which is required for this talk. And I think like everyone has this prerequisite, like most of you have this prerequisite, so we can skip this. So let's just start with fully homomorphic encryption. What is homomorphic encryption? Basically, it allows us to perform computation on the encrypted data. So let's say we have like 2 plain texts, X and Y, and we have like the encrypted version of them. We don't have the actual X and Y values. With homomorphic algorithms, we can perform computation on this encrypted data, and the computation would be in such a way that if we decrypt that particular encrypted data, which we have obtained after computation, the result would be consistent if we have like performed that particular operation on the plain text, which is kind of like fairly visible like from this diagram. So homomorphic encryption, fully homomorphic encryption in general is kind of like, I think is paradigm altering. Basically like it unfolds multiple use cases wherever you need to work with private or like sensitive information. Basically like you can offload all the computationally heavy tasks to a third-party server, and basically like the third-party server which is basically performing some computation on your data won't be able to learn anything about the actual data and still be able to like perform computation on top of it. So like here are like few use cases, like you can deal with health data, you can work with government data, financial data. You just basically send the plain text in the encrypted format. The third-party server will be basically performing computation on top of that encrypted data and will return the computation results. And once you have the computation results with you, you can just decrypt it, and like you have like f of m, which is basically the computation over the actual plain text. So I think like it's paradigm altering. We maybe have like, it may have like certain potential to basically alter the working of our existing protocol. We might have in future the end-to-end encryption systems, basically transitioning from the phase of HTTPS, HTTP secure, to HTTPZ, end-to-end encrypted. So let's start with the types of encryption basically. So like this is pretty ambiguous. Certain cryptographers try to divide the types of encryption among like 3 to 4 things, but I tried to keep it at like a total of 3 different categories. One is partial homomorphic encryption, second we have leveled, and third we have like fully homomorphic encryption. In case of partial homomorphic encryption, the algorithm might support either addition or multiplication, but not both the elements. And in leveled homomorphic encryption, you can perform addition and multiplication, but up to a certain number of time. The algorithm support computation with the addition and multiplication operation, but up to a certain limit of time. I will explain like what leveled homomorphic encryption, what's the actual meaning of leveled homomorphic encryption maybe in the future few slides. So just like for now, like keep it to yourself that with leveled homomorphic encryption, we can perform the computation like up to a certain number of times only. And similarly with fully homomorphic encryption, as the name dictates, we can perform the operation arbitrary number of times. So these are certain examples of different like encryption schemes. For partial homomorphic encryption, we have like Palier, RSA crypto systems. For leveled, we have like BFE, BGB, CKKS. Although this leveled homomorphic encryption systems have been like converted into fully homomorphic encryption systems based on the development taking place and like certain new results coming up. And similarly, we are like for a fully homomorphic encryption system, the most optimized system currently we have like is TFHE. We will be learning about TFHE like in the next few slides. So let's just look into the time frame. This time frame has been like developed by Zama. So like I just quoted Zama like for the time frame. And like on a broad level, there are total 4 branches of like encryption systems. Like first is over the integers branch, second is level scheme branch, third one is fast bootstrapping, fourth is like anti-RU branch. So in the time frame of the last 40 years, like as you can see from 1978 to 2009, there hasn't been much development in the homomorphic encryption space. But in 2009, Gentry came up with an algorithm called bootstrapping. We'll be learning about that algorithm like in the next slides. That particular bootstrapping algorithm kind of like brought a breakthrough in fully homomorphic encryption algorithms. And from that particular point of time, we can see how a lot of branches coming out. So if you want to perform like some computation over the integers, you can use the DJHV scheme. But DJHV scheme is like currently not used in production. And like similarly, if you want to work with level scheme branches, where the number of computation are fixed, then you can work with BGV, BFV, and CKKS scheme. And we will be learning in brief about all the BGV, BFV, CKKS scheme in the next slides. Similarly, if your encryption system is based on the NTRU problem, then basically the LTV scheme is for you. And similarly, like if you want fast bootstrapping, basically perform computation on the encrypted data for the arbitrary number of times, then we have this scheme CSW, FEHW, and TFHE, Torus for the homomorphic encryption. So let's just start with the basis of all these algorithms. Like, so basically we have lattice hardness problem, which basically kind of like enables researchers and cryptographers to have like an hardness idea, like how much hard it is to break this encryption algorithms. So all these encryption algorithms, most of these encryption algorithms, BFE, BGV, CKKS, TFHE, are based on this lattice hardness problem. So like if you are able to break this lattice hardness problem, then like the homomorphic encryption systems are being like broken. So let's just learn a brief about lattice-based cryptography. So lattice is nothing just like a bunch of points, and like you have 2 basis vector. Like here we have 2 basis vector. One is red one, another is blue one. And for now the coordinates are the whole numbers. So to build a lattice, what you would be doing is you would be basically creating certain combinations of those basis vectors. So like as in this diagram, like previously we had these 2 basis vectors, right? The red one and the blue one. Now what we are doing is we basically made the combination of 2 red vectors and 1 blue vector. So with this combination, we got this lattice point. And similarly, we can generate the multiple lattice point with the multiple different combination of these basis vectors. Similarly, like if you basically kind of try to extrapolate the number of combinations of this basis vector, you will get this lattice. Lattice is just like the points which have been like formed with the linear combination of these basis vectors. So what's the problem is? The problem here lies, suppose like if you are given this 2 basis vector, let's say the one which coordinates with 2913 and another with 7638. Now the problem is you have to find a point which is basically closest to the origin. So basically you will have to find the combination of this basis vector which correspond to a lattice point which is closest to the origin. And this problem even gets harder like when you introduce certain random points. Let's say I'm saying that I want to find a lattice point which is closest to a particular point. That might increase its hardness, and to increase its hardness even further, we can introduce multiple dimensions. Currently, we are playing around with only 2 dimensions, but let's say if we increase it to multiple n number of dimensions, then the problem gets even more harder. So the problem gets even harder with the increase in dimension. So this problem, so currently like researchers and cryptographers don't know any efficient algorithm or any efficient way to basically solve this particular problem. So we can say it's conjectured to be hard right now. And this algorithm is like post-quantum secure. So because like we don't have the efficient algorithms to solve it. So as in the previous time frame, we basically looked on a high level, like different encryption schemes and different encryption algorithms which lies on the schemes. So let's just talk about the few of the encryption schemes which are like based on the level homomorphic encryption and fully homomorphic encryption, the fast bootstrapping one. The first one is like BJB BFE. These both schemes are based on LW encryption problem. LW encryption problem is like another derivative of like lattice hardness cryptography problem, which we just previously saw. And this particular encryption scheme works to encrypt integer under a certain modulus and until a certain depth, as we have seen in the time frame that this BFE and BGB scheme basically lies in the leveled homomorphic encryption scheme category. Similarly, we have like CKK scheme. It's again based on the RLW encryption problem, which is basically derived its hardness from the lattice-based cryptography. And we can use this scheme to basically encrypt the real and complex numbers. And it also can like perform the computation up to a certain that basically it's again a level homomorphic encryption scheme. But we have like certain advancement with both CKKS and BFE BGB. Right now, we can use it for like n depth. We don't have like any depth constraint with them right now. But even we don't have like certain depth constraint with them right now. But this scheme, if we wanna use for like arbitrary number of computation, it's pretty inefficient. Similarly, we have like FHE scheme, which basically like utilizes a combination of like these different algorithms, LW, RW, and GSW. Both of these algorithms are based on like kind of like derive their hardness from lattice-based cryptography, and it basically uses the combination of this algorithm to encrypt the data. And again, like with this TFHE algorithm, we can encrypt the integers under certain modulus and perform the computation over the encrypted data for the arbitrary number of time, because like it supports bootstrapping, fast bootstrapping. We'll be learning more about bootstrapping in the next slide. So for now, just have a clear idea that TFHE have fast bootstrapping and we can perform arbitrary number of computation with it. So like there are, according to me, like these are probably the three main components of any encryption algorithm. First is the encryption itself. Second is the encoding of message. Encoding of message here basically conveys the idea of where we are actually representing our message inside a ciphertext. So let's say we have our ciphertext and we try to represent in the form of bits, let's say 0, 1, 0, 1, 0, 1. And now in that particular bitwise representation where actually our plain text is lying. So that's kind of like a high level idea of what encoding of message could look like. And similarly, we have bootstrapping. Bootstrapping is a way to reduce noise from a ciphertext. Yeah, so we have like this different encryption times: learning with error, ring learning with error, gantries, high orders. So the ring learning with errors is again just a generalization over learning with error. Similarly, when we try to increase the dimension over ring learning with error, we get the GSW. Probably Jay would be covering about TFHE and this learning with error encryption scheme. So in his talk, you can learn about this encryption scheme more. So I'll probably skip it right now. So yeah, like I'm just trying to cover the generalization over here. So we have like LWE, and then we try to generalize LW. So we got RLW, and then what we did is we basically expanded the dimensions of RW. Then we got GSW. And with GLW, we basically generalize the combination of LW and RLW. Then we got a GLW, which is much more harder. And then we try to generalize the GSW scheme, which is basically just a higher dimension version of RLW. Then we got this GGSW. So, and this GGSW scheme has been used in TFHE because like we rely on the combination of multiple encryption systems. So different encoding techniques. Let's see like how does the plain text actually looks like in the ciphertext. So consider like the whole bits is basically your ciphertext. So in case of like learning with encryption system, this is the ciphertext which we received. This is not exactly the ciphertext we received, kind of like a modified version of it, but you can basically like for now consider it as the ciphertext. And in this ciphertext, the message basically lies in the first few bits only, and the rest error lies on the the foremost right hand side of the error. And in this particular encoding scheme, if we want to perform computation, we'll have to every time perform the modulus of P with this particular AM values and C values such that the boundary of M remains inside. Basically, we just have to do certain modular arithmetics after performing the computation again and again. And similarly, we have like encoding in MSB with padding. So let's suppose if you don't want to do this modular arithmetic taking modulus again and again. So what you can do is you can just left certain bits, left certain space bits over here, so that like after performing computation, the plain text can occupy certain space on the left hand side. So it's again like the encoding of MSB, encoding in MSB with padding of bits. So now let's talk about bootstrapping. So as I had previously conveyed the idea that TFHE like suppose the fast bootstrapping algorithm through which we can perform the computation on the ciphertext data any number of times. So let me start with the basis of bootstrapping, like why we actually need bootstrapping. In the meanwhile, like if you guys have any questions, like feel free to stop me. Like I want to keep this session like as informal as possible. So yeah. You can also like share one of the mic, I think. Hmm.
I had one question.
Oh, okay.
Slide number 11.
Oh, sure. This one?
No,
The slide.
status,
Yeah. Okay.
So I do not have much idea about how this status thing works, but you could clarify me. Like how does this? Which point of the lattice is closest to the origin? Like how this is a difficult problem to solve?
So basically, like for now, you have only 2 vectors, right? And you can have like multiple 3 to 4 vectors, and every vector could have like the different number of dimensions. So you would have to construct this combination. Let's say like adding the red vector 3 times, then subtracting it with the blue vector, then basically like performing certain other computation like with other basis vector, and getting to this point, and this point is basically closest to the origin, right? So we'll have to find that particular linear combination of the basis vector which corresponds to a point which is closest to the origin.
So the issue about having the hardness is that you can think of entire. Let's just imagine two-dimensional. Let's just imagine two-dimensional, and what you eventually have is that you draw a vector, right? And you increase the dimensions, you can have your vectors, and you have a basis, and you increase the dimensions, and you have vectors. Now, the problem in this case is that if I give you a point in this dimension, like you can imagine n-dimensional stuff. If I give you a point, your job is to find the closest vector using the basis that I've given you.
So my job is to find the
Closest vector to that thing using the basis that I've given you.
Okay.
And that is hard as you increase the dimensions.
Mm-hmm.
Does that give you the intention, or should I draw something?
Yeah, we have like whiteboard.
Should I?
We will
okay,
love to use this.
I'm sorry for intervening in your talk. So the way it works is that you've got this. This is a two-dimensional thing. You've got a basis. Let's say this is your first basis and this is your second basis, right? Now you can construct a vector out of it. Like you could just add it certain times, add this certain times, and you will find a point. Now I'll tell you that I have a point that is this. Your job is to find the closest vector that can be constructed using this basis that would be as closest to this. Right? And this is known as shortest vector problem. And this is, turns out, finding this as dimensions increase is as hard as sys, which is short integer solution.
Mm.
Yeah. Short integer solution. Okay. So this is not exact, but the problem that we have over here is that we need to find the shortest vector to this thing. And turns out doing that is really hard as you increase the dimensions. That's it.
Thanks.
So what does it mean when we talk about noise as a part of the ciphertext?
Mhm.
Why isn't it deterministic? Why do we have noise?
Why do we have noise? Do you want to explain? Do you want to show the correlation of like the lattice cryptography and the noise with them?
Yeah, so noise is this. So what I start with a message that gives us a point near this, but I add noise so that the real point that you get as a person who's getting the ciphertext is near the basis vector.
Okay.
Okay.
So you're not simply giving me the point. Actually,
Yeah, I'm giving you a ciphertext, which I claim to be somewhere near this. Like for example, I'm giving you a ciphertext. I'm constructing a ciphertext, which would be near this point, but I'm giving you this point, and the noise comes from here. So I create the ciphertext. It comes over here, and then I add noise. So that for you, it's really, really hard unless you know some secret to get back to this.
Gotcha.
Got it? That's where the noise comes from. That is why noise is pretty important for the security of the scheme.
Maybe like you can understand in a way like maybe let's say we have a polynomial. Let's say ax plus by plus c equals to let's say z. And we added noise to the RHS part of it, let's say z plus c. And now what I am doing is I'm basically, now this ax plus by plus z plus c is actually my public information. Okay? And the only solution of this vector of this problem is x plus by plus c plus x plus by plus cz equal to, let me just use the board maybe. Let's suppose like we had a polynomial ax plus by plus cz equals to let's say k. Okay, and we had like certain solution of it like s1, s2, s3. Okay, and let's just assume like this solution of this particular polynomial is the private key, and this polynomial is actually the public information. And now what we would be doing is we would be encrypting the certain data with, let's say I'm adding an error with this particular k property, let's say k plus e, and let's mark it that k plus e is at k dash. So now what we have like ax plus by plus cz equals to k dash. And now let's say like if I want to encrypt something, I will use this polynomial to encrypt it. And now a user which actually holds this private key can basically put all these values inside this, and he will receive k. And a malicious user, like if he's trying to find the solutions of this particular polynomial, won't be able to find it because like we have k dash over here. And like if you know this private key, you can find k, and you have k dash, so basically you can actually find the noise over it. So that's sort of a correlation. Any more questions? Okay, then maybe we can start with the bootstrapping algorithm then. So as we had discussed noise over here. So with bootstrapping, what we try to do is like as we perform more and more computation over in the encrypted data, the noise starts increasing. And at a particular point, so as you can see like in this picture, so like if we perform certain computation on this particular data, the noise will start increasing, right? The error will start flowing in the left hand side, just basically occupy the MSB bits. So what we perform is we basically use the bootstrapping techniques, which basically helps us to refresh the noise of that particular ciphertext. So what we actually do in the bootstrapping algorithm is, let's say we have X, which is basically a plain text encrypted with certain private key, and has achieved the level of noise, this level of noise. And if we perform any more computation over this ciphertext, then the noise might increase over this red counter as well. Like if the noise increases over that particular red counter, then we won't be able to decrypt ciphertext properly. So what we did is we basically encrypted this ciphertext under certain key k dash, which is basically you can see this green encryption over the actual encrypted data. And what we did is we basically also encrypted the secret key of this particular algorithm, and under the green secret key. So now we have this like encrypted data, and now we are calling this encrypted data as the bootstrapping public key. Now what we will be doing, as we are doing this thing homomorphically, so we can basically open this green box with the open this blue box with this blue key in which has been encrypted with the green secret key. And what we do is we basically inside this green box we open this blue box, and now what we have this plain text encrypted with this particular green secret key. So with bootstrapping we basically reduce the ciphertext noise, and like previously this green box has this much amount of noise, so the finally X would be having like certain amount of noise which is like lesser than it should be. So with TFHE, we gets the programmable bootstrapping. And what programmable bootstrapping in general means is like basically while doing bootstrapping, we can perform like, we can have any univariate function operate on the ciphertext. So basically like it's kind of like a flexibility we get with the programmable bootstrapping is basically we can like freely perform any like computation of any particular univariate function on the ciphertext. Like, you're familiar with univariate, multivariate functions, right? Univariate functions are nothing like just the functions which basically involves only a single type of variable, and multivariate functions are like in which like we have like different number of variables. And if you need to apply like a multivariate function on this hypertext, you can just represent it as a linear combination of the multiple univariate functions. So yeah, that's on the programmable bootstrapping. Like, and yeah, we have like lots of open source implementation of these libraries. Like recently, Jay also like implemented BFE scheme and Rust. You should also try check out that. And yeah, these are the few open source implementation. And these are the like current projects in space: Zama, Phoenix, Inconet. We have like Inconet Remy from Inconetwork over here who would be giving talk next. So like, if you wanna explore this space, like with respect to blockchain, these are the projects which you can look out. I will be sharing the slides so you don't have to take pictures or like. If you want to take picture, you can take that. And yeah, like these are the sources. So yeah, that's it, my talk. Thanks for listening.
Any questions, guys?
Yeah, for sure.
Okay, so this might be a little bit trivial, but so I got the intuition of why the lattice problem is hard. But how do you go from the lattice problem's hardness to creating homomorphic encryption protocol?
Yeah.
Okay, thank you.
Jay will be covering. Yeah. Yeah, anybody like implementation related question maybe like how can you start working with this FHE thing with like with respect to blockchain, like start creating encrypted smart contracts. Yeah, all those questions would be covered by Remy, I think so. It would be better he would answer those.